So welcome back everyone. I am Dr. Rajesh Singh and this is part 3 of the video solutions for exercises for section 4.1 of the book Introduction to Real Analysis by Bartle and Sherbert. In part 1 and 2 we have solved question 1 to 14. So in this video we will solve question number 15, 16 and 17. So let us start with question number 15. So in this question we have been given that fx is equal to x when x is rational and 0 when x is irrational. So it is Dirichlet function and we have to show that it has limit at x equal to 0, and if x is not equal to if c is not equal to 0, then f does not have a limit at c. That is, we have to show that f has limit only at x equal to 0. So let us start with question number 15. So we have been given that fx is equal to x if x is rational and 0 if x is irrational. So we have to show f has limit only at x equal to 0. So in this case, first we will show that f has limit at x equal to 0, and then we will show that at all other points limit does not exist. So what we will do, we will take this. So first we will show that f has limit at x equal to 0. So first we will show that f has limit at x equal to 0. So for this we assume epsilon greater than 0 to be any real number. So we are taking epsilon to be any real number. Then we have to show there exists delta greater than 0 such that 0 less than x minus 0 less than delta should imply fx minus 0 is less than epsilon. We will show that f has limit 0 at x equal to 0. This we will show that f has limit 0 at x equal to 0. So start. Consider fx minus 0. So this is equal to, I will use one observation that so this is equal to mod fx, and mod fx is always less than equal to x. This is the observation because our fx is either x or 0. So mod fx is equal to either mod x or 0, and 0 is always less than equal to mod x. So fx is less than equal to mod x by definition of fx. This is the trick. This is observation that we have to remember, that mod fx is less than equal to mod x. Now mod x I can write as x minus 0. So from here it is clear that if I take delta equal to epsilon, then we will have 0 less than x minus 0 less than delta will imply fx minus 0 less than epsilon. So take delta equal to epsilon, then by the choice of delta it is clear that 0 less than x minus c less than delta x minus 0 less than delta implies fx minus 0 is less than epsilon. Hence limit x tends to 0 fx is equal to 0. So this we have shown. We have shown that at x equal to 0 f has limit and it equals 0. Now we have to show that if I take any other point c not equal to 0, then I will have, then limit will not exist at that point c. So let c not equal to 0 be any point in our claim. What we are going to show, f does not have limit at x equal to c. F does not have limit at x equal to c. So for this what we will do, we will assume, we will take two cases. Case 1, C belongs to Q. Then C is a limit point of Q complement, and therefore there exists a sequence Xn in Q complement such that Xn converges to C. Or we can directly prove this. We don't need to take the cases. What we can do is we can directly do both the cases together. So what we will do now, since C is a limit point of both Q and Q complement, so there exist sequences Xn in Q and Xyn in Q complement such that Xn is not equal to C for all n, Yn is not equal to C for all n, and Xn converges to C and Yn converges to C. So we have this Xn is a sequence of rationals which is converging to C, and Yn is a sequence of irrationals which is converging to C. So f of Xn is now f of Xn is equal to Xn for all n belonging to n, and f of Yn is equal to 0 for all n belonging to n. So this implies f of Xn is nothing but the sequence Xn which converges to C, and f of Yn is equal to constant sequence 0, so which converges to 0. Thus, since C is not equal to 0, we have two sequences Xn converging to C and Yn converging to C such that the corresponding sequences Fxn and Fyn converges to different limit. So by sequential criteria for limits, limit x tends to C, fx does not exist in R. So this is how you prove that the Dirichlet function x0, x at rationals and 0 at irrationals will have limit only at x equal to 0. Now I want to show that how you do such type of questions. There will be other form of such questions. So how you will do these questions. So suppose I have been given another function f defined from R to R as f of x is equal to 2x if x is rational and x plus 3 if x is irrational. So what you do to find the points at which the limit exists, find all points in R such that find all points C in R such that limit x tends to C, fx exists in R. So to find such points, what you will do, you just equate these two. So when you will equate these two, So in this case 2x equal to x plus 3 will give you x equal to 3. So this is the point at which function will have limit, and at all other points the function will not have limit. So we will show that. So first we shall show. So first we will show that f has limit 6 at x equal to 3. So 6 I am finding by putting x equal to 3 in one of the two values. So to show this, let epsilon greater than 0 be any real number. So to show there exists delta greater than 0 such that 0 is less than x minus c less than delta implies fx minus fx, so c is given to be 3, fx minus 6 is less than epsilon. So for this consider fx minus 6. So fx I can write it like this. It is 2x minus 6 if x is rational, and x plus 3 minus 6 if x is irrational. And if I will solve this further, I will get 2 times x minus 3 if x is rational, and this is x minus 3 if x is irrational. So obviously I can write this to be less than equal to 2 times x minus 3. So what delta we should take? Let delta equal to epsilon minimum epsilon by 2. So then for the above choice of delta, it is clear that 0 less than x minus c less than delta x minus 3 less than delta implies fx minus 6 is less than epsilon. Hence limit x tends to 3 fx is equal to 6. So this we have proved. Now we will show that any c not equal to 3, if c is any point not equal to 3, then limit x tends to c, fx does not exist in R. So next, if c is not equal to 3, then we show that limit x tends to c, fx does not exist in R. So for this, what we will do, we let, since c is limit point of both q and q complement, so there exists sequences xn in q with xn not equal to c for all n, and yn in q complement with yn not equal to c for all n, such that what is happening, such that xn converges to c and yn also converges to c. So we have found two sequences, both are converging to c. Let us look at their corresponding subsequence. So let us look at f of xn. Now f of xn, so f of xn is equal to 2 times xn for all n belonging to n. So f of xn converges to C, since xn converges to C. Also, f of yn is equal to yn plus 3 for all n belonging to n. So f of yn converges to C plus 3 since yn converges to C. Now as C is not equal to 3, so 2C is not equal to C plus 3. Consequently, we are able to find two sequences xn and yn both converging to C such that their corresponding sequences fxn and fyn converges to different limits. Hence, by sequential criteria for limits, limit x tends to C, fx does not exist in R. So this is the proof of this question. So whenever we are given Dirichlet type of question, we just need to equate the function for rational with the function for irrational, and we have to find the points at which the two are intersecting, and then we will claim that the limit exists only at those points, and at other points limit will not exist. So this is how we have to deal with these Dirichlet type of questions. So such questions are very important because generally one type of this question is there in the examination paper. So let us now look at next question, question number 16. So what is question number 16 here? Question number 16 is f is a function from R to R, I is any open interval in R, and C is any point in I. F1 is the restriction of f to I, and we have to show that f1 has limit at C if and only if f has limit at C and the limits are equal. So question number 16, given f is a function from R to R, I open interval, f1 is equal to f restricted to I. So this is function from I to I such that f1x is equal to fx for all x belonging to I. So this is how restriction functions are defined. Restriction functions are nothing but we take the function on some subdomain of the domain of the function. So f1 and f coincides with each other on I. So f1 is given to be this to show limit x tends to C f1 x exists if and only if limit x tends to C fx exists, and in such case limit x tends to C f1x is equal to limit x tends to C fx. So the solution, we first assume that limit x tends to C f1x exists and equals say L. So we are assuming this to show limit fx exists and equals. So let epsilon greater than 0 be any real number. So we have to show there exists delta greater than 0 such that 0 less than x minus c less than delta implies fx minus L is less than epsilon. So for this we have to find some delta such that 0 less than x minus c less than delta implies fx minus L is less than epsilon. So for this what we will do, we will use the limit of f1x. So since limit x tends to c, f1x is equal to L so there exists delta star greater than 0 such that 0 less than x minus c less than delta star and x belonging to ai, because I is the domain of f1. So x belonging to I implies f1x minus L is less than epsilon. f1x is equal to fx. So this implies 0 less than x minus c less than delta star and x belonging to I implies fx minus L is less than epsilon. Since for all x belonging to I, f1x is equal to fx. So now to prove this part, to prove first part, we just have to remove this condition. We just have to remove, because domain of f is complete R, so we have to remove this. So somehow we have to choose our delta so that this gets removed. So we want to remove this. So what we will do, we will take delta equal to minimum of delta star c minus a by 2 and b minus c by 2, where I is equal to AB. So I am assuming that I is equal to AB. So I am taking delta equal to minimum of delta star C minus A by 2, B minus C by 2. Then 0 less than X minus C less than delta implies, what does this imply? That 0 is less than X minus C less than delta, and because delta is less than equal to delta star and X belongs to I, because what we have done, this is A, this is B, so this is Ri, this is somewhere C. So I am taking distance half this distance. Delta is smaller than this and delta is smaller than this. So if I take x minus c less than delta, so it will be x will be somewhere here. So it will be within the interval x belonging to I. So by this choice of delta, if 0 is less than x minus c less than delta, then it should imply 0 is less than x minus c less than delta star and x belongs to I. So from this star, so this implies fx minus L is less than epsilon using star. So hence, by the above choice of delta, we have 0 less than x minus c less than delta implies fx minus L is less than epsilon. Hence, limit x tends to c, fx is equal to 1. Now we have to proceed with the converse part. Conversely, assume that limit x tends to c, fx exists and equals, say, L. we have to show limit x tends to c f1x exists and equals L. So this is what we have to show. So for this, what we will do, we will take let epsilon greater than 0 be any real number. So we have to show there exists delta greater than 0 such that 0 less than x minus c less than delta and x belonging to I implies f1x minus L is less than epsilon. So this is what we have to show. So let us start now. Now since limit x tends to c fx is equal to L, so for above epsilon greater than 0 there exists delta star greater than 0 such that 0 less than x minus c less than delta star implies fx minus L is less than epsilon. So what we will do, this is our star. So what we will do, we will choose delta equal to delta star. Now 0 less than x minus c less than delta and x belonging to I implies 0 is less than x minus c less than delta and delta star and x belongs to I, and this implies from this we have fx minus L is less than epsilon and x belongs to using star. Now because x belongs to I, so fx is equal to f1x. f1x minus L is less than epsilon since x belonging to I implies f1x is equal to fx. So hence we have delta greater than 0 such that 0 less than x minus c less than delta and x belonging to I implies f1x minus L is less than epsilon. So thus limit x tends to c f1x is equal to L. So this proves the question number 16 that limit x tends to c f1x is equal to fx. In the question it was given that I was an open interval, so where we have used the condition that I is open. If you look at the proof where we have used I to be open, so at this place choosing delta, this was greater than 0 because I was open, otherwise it may fail to be greater than 0, because if I take c equal to a or c equal to b, then I cannot choose such type of delta. So in the proof I have used the openness of I at this place, right? So now let us move to the next question, which is question number 17. And what is question number 17? Question number 17 is this. So f is a function from R to R, J is the closed in J be a closed interval in R and C is any point in J. If F2 is the restriction of F to J, show that if F has a limit at C, then F2 has a limit at C, and show by example that it does not follow that if F2 has a limit at C, then F has a limit at C. So question number 17, we are given that F is a function from R to R, J is closed interval say AB, it is given to be closed, and f2 is equal to f restricted to j, that is it is a function from j to j such that f2x is equal to fx for all x belonging to j. To show limit x tends to c, fx exists implies limit x tends to c, f2x, and in this case the two limits are equal, and then we have to show that limit x tends to c, f2x exists need not imply limit x tends to c, fx exists. So for this we have to give an example, and this part I am leaving because it is similar to the converse part of the last question. So this is the converse. From here you can, because we have nowhere used the condition of openness here, so straight this converse part of the proof can be copied as it is. So I am leaving this part. So this part I am assuming that you all can write this part. So we will give an example here only. So we will just give an example to show that limit x tends to c, f2x exists need not imply limit x tends to c, fx exists. So for this we have to define a function, define f from R to R as fx equal to 1 if x belongs to 0 1 and fx equal to 2 if x does not belong to 0 1, and let j here is equal to 0 1 close interval and f2 be the restriction of f on j, that is f2 is a function from j to j defined as f2x is equal to fx, which is equal to 1 for all x belonging to j. So f2 is a constant function. First we will show that limit x tends to 0, f2x exists. So for this, let epsilon greater than 0 be any real number. Now consider first we will show that this is exactly equal to 1. So this we will show. So consider f2x minus 1. So this is equal to 1 minus 1 for all x belonging to j. So this is equal to 0 for all x belonging to j. For any delta greater than 0, 0 less than x minus 0 less than delta implies less than delta, and x belonging to j implies f2x minus 1 is less than epsilon. This is less than epsilon for all x belonging to j, whatever delta we may take. So hence limit x tends to 0, f2x is equal to 1. So f2 limit x tends to 0, f2x exists. Now we will show that limit x tends to 0, fx does not exist. So for this we have to give an epsilon greater than 0. So what we will do, we will or we can construct a sequence. So we will use the divergence criteria to give let xn equal to minus 1 by n for all n belonging to n, then xn does not belongs to j for all n belonging to n. So this implies f of xn is equal to 2 for all n belonging to n, and this implies f of xn converges to 2. Now take yn equal to 1 by n for all n belonging to n. So then yn belongs to j for all n belonging to n, and this implies f of yn is equal to 1 for all n belonging to n, and this implies f of yn converges to 1. Thus we are able to get two sequences xn and yn in R such that xn is not equal to 0, yn is not equal to 0 for all n belonging to n, xn converges to c 0 and yn converges to 0, but the corresponding sequences f of xn and f of yn converges to different limits. Hence, by sequential criteria for limits, limit x tends to 0, fx does not exist. So we have shown that limit x tends to 0, f2 exists, but limit x tends to 0, fx does not exist. So this is the proof of question number 17. So we have completed all the questions of exercise 4.1. So thank you.